looks great.
Okay, thanks. Yeah. So basically today I'll be talking about conversational recommender system using deep reinforcement learning. And the overall agenda is that I'll quickly cover some of the terminologies for reinforcement learning. And then we'll cover basic terminologies here. And as and when we talk about the other approaches, I'll basically go deep into it. So first I'll cover some of the foundations, what are the value functions, what is the deep Q network, reinforced algorithm, etc. And then we'll jump into various papers and I listed them here. So let us get into first the deep learning foundation. So basically reinforcement learning is different compared to deep learning. As you may know that there is it is more of a trial and error kind of system. So if we have to, if I had to give an analogy to a common man, it is like riding a bicycle. So if you tell someone that you have to just sit on the bicycle and turn 30-degree left and push the pedal, half of the pedal, and then again move forward. And if you move bend, move right. So those kind of instructions, whatever instruction you give in theory are not at all helpful unless the person will actually go onto the bike and try himself and learn from whatever goes well and whatever fails. So this is basically the common environment for reinforcement learning. It's more of a trial and error. Now from terminology point of view, this world which is represented is an environment, and the brain which is represented is an agent. And so basically this is, I think, very critical to understand the differences between various terminologies and how they basically correlate. So agent, which is, let us say, a human being, he basically executes some action. So let me take an example of, let's say, playing a game. Okay, either you go north, south, east, west, you just take an action. And then based on that, you will see from the game, the output. So what the agent will be able to do is agent will be able to just observe how the environment behaved with respect to this action. It is not that whatever the reward which will get which the agent will get from the environment. So I'll spend a little bit more time here because this has to be conceptually very clear. So for example, the agent, when let us say he moves the cursor up many times and he hits a gold and then he gets a gold, otherwise he doesn't get a gold. So the idea here is that the agent, the key concept is agent doesn't know completely about the environment. Agent only knows that, okay, in this position, the environment is like this, and this is the reward I got. So in case of reinforcement learning, what happens is the agent keeps trying various actions, keep getting different rewards in anticipation that the environment right now is like this. And based on that, it keeps on doing this iteratively. So this is the basic reinforcement learning setup. Now, if you go into the details, so reward is basically how well the agent is doing. So, and if it's not doing well, some people use penalty also, but lower reward is equal to penalty. And at each step T, the agent executes an action. It receives an observation OT at a point in time, and then it receives a reward. So this is the sequence which I mentioned. The concept which I mentioned earlier was agent doesn't have complete information about how the environment is. It only receives the same way environment also only receives the actions AT. It emits the observation based on which the agent decides what is the next action I should take, and it gets the reward also. And this keeps on happening. Now, I may not I'll quickly walk through some of these slides because I may not go into all the mathematical details. So the first is the state. Now, what is the history? So history is more of a state of actions which you take. So let us say if you are going from walking from point A to point B, you go on a road, you go straight, then take left, then go further straight, then take right. So all the observations which are there all observations which are like O1 and what is the reward which we got. So basically when an agent gets simultaneously two things, it gets the reward, observation, and it gets the reward. So history is basically a collection of observation, reward, and action, previous action. And then again, it goes to the next future timestamp. And state is basically the information used to determine what happens next. So if there is any question, then maybe I can go to the environment state. So as I mentioned, environment state is basically it's a private representation. The agent doesn't know what the full environment looks like. And again, the environment state is not visible to the agent. And even if the state is visible, it may contain irrelevant information. So even though the state which is visible to the agent, it may not contain the right information. So when the agent is learning through the environment, agent has to keep these things in mind. The next one is the agent's state. Now here, again, agent states in the internal representation. The way an agent doesn't know about environment, same way environment doesn't know about the agent. So it is the information which is used by reinforcement learning algorithm. So after that, we talk about, because this is more of a sequential decision-making process, where you take one decision, then you go to the next state, then there you take again another decision, and then go to the next state. So in case of Markov property, what is being said is that the next state ST plus 1, it is not dependent on all the states S1 to ST, but it is only dependent on ST. So this is the Markov property. And what does it mean is that the future is dependent of the past given the present. So we don't need to know about the whole past. Only the present state, this one, is good enough for us to move further. So this Markov property has been very helpful, and it has helped in coming up with some of the mathematical models so that you can model a complex environment. Now, coming back to environment could be partially observable, or it could be fully observable. Meaning is that agent is able to directly see the environment's state, but this is in practice not true. We don't have any environment where agent can know completely about the environment. In that case, we already know what needs to be done. So the next thing is that the practical situation is partially observable environment. So agent only knows indirectly about the environment. It doesn't have any insight into the internal of the environment. So if we talk about basically when we talk about a robot, when it's a camera is actually looking at something, it is only what the camera is projecting there. And if let's say the camera is at height, then you cannot identify what was the distance between the robot and that particular object. So, so this is a very important concept, partially observable Markov decision process, and many of the formulations which we'll cover later are actually just done based on this. So after covering like some of the theory now, the question is then how does what an RL agent looks like. So in this case, if we see the RL agent looks like basically three components. Now we are going down into like trying to mathematically modeling this kind of environment. So here we say that it is first is the policy. So how will the agent behave? So as and when the agent is learning, it will form a policy in its mind, whether based on rewards and the penalties. And again, if it sees the same thing in future, it will behave wherever the reward is higher. So that will be one part which will be part of the agent. The second is the value function. Now agent, when we see further maze examples in future, it's that in whichever state you are, is it a good state or is it a bad state? Or are you taking the action which is good, or are you taking the action which is bad? And it is represented by a number. So here the value function will be for both state and action. And the last is the model, which is agent's representation of the environment. Now, model is what the agent will actually start creating based on what the environment is, what observations environment is presenting to it. So these are the components. I'll go further into policy, value, and model. So policy is basically the agent's behavior, as you have seen, and it is a map from state to action. So this is like here, when the agent was there, it actually saw the state of the environment, and then it took the action. So this is basically the policy. So policy is a map from state to action, and a policy could be deterministic or it could be stochastic. Deterministic policy is going to always take the same step, same action. In case of stochastic, it may change a different action, even though the observer. So basically, in case of deterministic, the agent will take the same action every time. In case of stochasticity, even though the state is like same S1 or S2, the agent may decide to take a different action. So this is from policy point of view. The second is from value function. So as I mentioned, there are value functions associated with both state and action, and it will say how good or bad the particular state is, or how good or bad the particular action is. And you would like to select the action which is best. Then here, basically, the model is, you can say, you can consider like a mind map, or the thinking about the environment, what the agent has developed is a model, and based on that mind map, it basically predicts what the environment is going to do next. And depending upon that, depending upon the reward state, previous actions, the agent will know now if I'm going to take this particular action now, how will basically the environment reward, what reward or state in which it will go, and let me take action according to that. So this is basically the model, and the model basically tries to predict the next state. So these were like some, now I think it will be more clear once we have some example. So here, in case of maze example, let us say the reward is -1 every time when the agent takes a step. So whether it goes to the right or the top and then right, but it only gets the positive reward when it reaches goal. So only goal has the positive reward. All other states are basically have a negative -1 rewards. So that is what is represented as rewards. Then in case of actions like, then in case of actions at any point in time, the agent may be able to take, say here, left turn, or it can go to north or south, but it cannot go right or east. So these are the possible, so all possible actions are not possible in each state. That is also one thing with the system has to model. And state is basically the agent's location. So agent will basically keep moving into various states and then try to reach the goal. Now, what is policy? So policy, as we saw here, is like agent's behavior function, how agent is going to behave. So in this case, the agent will be behaving, agent can behave in this particular example only as shown by the arrow. So here, if the policy is that only the agent can go, so this is like one of the policies. Here, the agent decided to go up, it could have even gone down also. So then that will become a different policy. So various possibilities in one particular state basically represent a policy. Now, from value function point of view, what is the value of each state? So if you see, we started with, let's say, the value function -16. And as you go further, you basically advance to like a positive side. Every time you take a step, you go, you add +1. And once you are near the goal, you are basically having like the maximum possible number. And as and when, like say you get into the wrong location, you get further penalty and it becomes, so this state is like, this minus 19 state is like the worst state to have, because there was no way, or sorry, minus 23, because this is the path from where you'll have to again trace back. But this was the path which was more looking like a positive path. So this actually indicates what is the value of the state and how good or bad that state is. So this is the example of the model. So in case of model, I mentioned earlier that for each step, the reward is -1. And basically using this from the initial starting state, you can keep moving here. So these were, I think I would like to, let me just check the time. What's the time now? I wanted to spend 20 minutes on that. So on the concept part. So here, this is the agent is basically have an internal model of the environment and how much reward we get from each state. The model will be initially very, very imperfect as it will start learning, but it will become it will become smarter over a period of time. So then one more thing is that how do you basically model this kind of environment? So as we saw that the partially observable Markov decision process is one of the mathematical formulation which is used for formulating these as the problem which can be solved. So in case of here, Markov decision process formally describes an environment. And so here fully observable we mean is that the current state can completely know about what the environment is. And all the RL problems can be formalized as the Markov decision process. Now, I think I already mentioned about this Markov property, which says that the future is independent of the past given the present. So basically, I just need to know the current state, which is ST. I don't need to know the states prior to that, which are ST minus 1, ST minus 2 up to S minus 1. The current state captures all the relevant information from the history. Once the state is known, the history can be thrown away, and this the state is sufficient statistic for the future. Now, Markov chain is basically a tuple, and here for each of the state, you will have the value associated with it. So what is the transition probability from one particular state to the other particular state? We will see an example, but what it says is that probability of transitioning from S to SDES is the probability of transitioning from S when the state was S to the next state T plus 1 when to the state S dash. So P is the state transition process. So basically Markov chain will contain the state as the nodes and the arrows as the transition probability. So here is an example of Markov chain with the transition probability. So let us say this is the life of a student, and he is in the class, looks at Facebook, or in the class, he falls asleep. He attends the class examination and then he passes off. So there are some states and the transition probabilities are there along with them. So I think you all may be familiar with it. So let's say if we talk about from C1 to C2, the probability is 0.5, which is represented as transition metric. Now here, I think it is the same information, but what is the reward? So you want to get the reward from here. So what is the reward that you will get if you transition from S to and there is a concept of discount factor. So basically, discount factor can be well explained here, that if you're taking an action here, going in this direction or this direction, because you are far away from goal, it is still okay. The penalty may not be very high. But if you are, let us say, here, and you are going down this path or this path. So when you are further, when you come all the way here, let's say here, if you have to move to -3 or -2, So when I'm taking a step here, I think immediate steps are more important for me rather than the future step. Let's say, for example, at 0.7, whether I'll go to at -7, I will go to 0.6, -6, or when I'm at 16 or 15, whether I'm going at -14, this is more important. So the gamma is the discounted factor. So immediate states basically get the higher are given. So that if the discount is 1, then all states are treated equally. If the discount is 0.5, then the immediate states have higher value, and the further states have the lower emphasis on making the reward. So this is also these similar kind of example. Maybe then I'll move to quickly to the few last terms. So reward and return are usually different but used interchangeably. But in case of return, what we could say is that in this example, so these are basically the rewards. So rewards you get at each step, but return basically will be the combination of all the steps which you have taken. So that is what is the return. So here, if you see, it says return GT is the total discounted reward from time step T. Now, so here, if we go, so here, if you're at state, this state, then the reward, cumulative reward will be calculated from here. If you are here, you'll just get the cumulative return you'll get the return up to here. So this is for all future steps, discounted reward, what you get is the return. And maybe I quickly mention about what discount is needed. Maybe I can skip this slide. Then I mentioned earlier that the value function. So state, and so how good the state is and how good the action is, those are basically represented by a number, and the state value function, so which will basically tell how good or bad the state is. And here then we talk about the same decision process. But now what happens is that a Markov decision process will consist of, it is a tuple which will consist of state, which is consist of action, and model, reward, and the discount factor. So this is how MDP is created. And I'll then go to the policy. So policy, as we mentioned earlier here in this example, this one policy. So there are various policies to reach this goal from start till end. So this is like one policy. The other one is like this one, you come back, you go down, and then again come back. So there are various policies which the system will actually compute. And so that is the reason for computing the this tuple is needed at each stage, because you're talking about different state, different set of state, different set of actions, models, different rewards, and also what is the discounting factor. So in this case, the reward function will be like at a state S, in what out of all set of actions, you took action A, and then what is the reward which you are getting while you're in state S, and you have taken action A. And discounted factor, as I mentioned, is between 0 and 1. So I'll skip this policy. So this is the policy which I mentioned. So I think this looks like it. So here, as I mentioned earlier, the state value functions and the action value functions. So basically, a value function will be that expected return, which is like G, when you're in state S and further onwards, starting from state S. The same way, the action value which you will get is the expected return starting from state S and the action which you have taken. So the difference between the state value function and action value function is that in case of state value function, the return is only dependent on the state. But in case of action value function, it is not only dependent on state, but what action you took on that particular state. So I'll skip this Bellman's expectation equation and then directly move on to now various approaches which are used the reinforcement learning method. So first, I'll talk about the first type, because this is more of a recommendation conference. What I'll do is I'll first talk about like how how other approaches apart from RLs have been taken up for building a conversational recommendation system. So here, so the in case of conversational recommendation system, I think I didn't describe what it is, but in case of normal standard recommendation system, what happens is that there are various attributes, user attributes, item attributes, and product descriptions and other side information are being used for providing the recommendation. But in case of a conversational system, it is more like a chat kind of environment where the recommendation system will actually try to understand. It will definitely have all the user information, item information, other information also. But during the chat, it will try to understand what are the other information the user is actually asking for or ask for the clarification. So once the system has good enough idea about what the system is, what the user is going to ask, the user is asking, then it will get into recommendation mode. So that is a difference. So in short, it will be a clarification mode earlier, understanding what the user wants, and then recommending. And it will be an interactive process. So here basically, I'm talking about this paper right now because there's no publicly available a large data set which was centered around the recommendation system. So the publishers of the paper have collected the 10,000 conversations, and this again for movie recommendation. And here the data set is used to explore multiple facets of conversational recommendation, and it will help in trying out new neural architectures. So again here, so it can help in solving the problem. In typically in recommendation system, you go all the way from sentiment analysis, cold start recommendation generation to detail aspect of how natural language is used in the real world. So there is a wide spectrum of how granular or how detailed you can go, or how higher or course you could be. So here, many of you may be familiar with this HRED hierarchical recommendation system. This doesn't, as I mentioned earlier, this paper doesn't use reinforcement learning, but I just wanted to set the stage that how without RL, people are trying to get into the deep conversational recommendation. So here, basically, in this case, this is more of a set of hierarchical LSTMs. So first here, these are the input queries like Cleveland Gallery, and then the user enters like Lake Art. And now, as you may be familiar, that in the standard LSTM architecture, this particular last state basically generate the representation of all of the queries. So this is the query level recurrent state. Same thing happens here also. Now with that, what is being done is that this SN11 information is being combined, and then using that, it goes to the decoder state, and then decoder then basically then start making the prediction. So this was a standard method which was used. The similar approach was actually tried for the conversational system. So here I can give an example where you can say the human is saying you can try Planet of the Apes. The older one is quite suspenseful and family friendly. So this is what the person is trying. The HRED model, which is the previous model, was not actually concerned with more of a deep conversational recommendation. Provided this, that I have seen that one yet, but I heard it was good. I haven't seen that one. Have you seen The Last House? So basically the recommendation wasn't, the output wasn't very good. But instead of that, if you see the new model about which we will talk, the deep conversational recommendation, actually The Force Awakens is also a good one, Return of the JD, all good movies. So this is where the better recommendation actually comes out of it. So how is the architecture here? So from architecture point of view, it is similar to that. It is similar to the hierarchical architecture, but there are the components which are very different. So first one, hierarchical encoder is basically similar one, which actually follows the HRED architecture. And then basically here, so now here, what will happen is the based on the final state, the system will generate a few options here, and then again this information also will go to the sentiment analysis. The sentiment analysis will also be done, and that actually goes to the auto encoder recommendation module. And the output of this auto encoder recommendation module again comes back to the switching decoder. And this information is then basically used. Not only the information from the hierarchical encoder, but the information from the sentiment analysis, and also the information which goes to the auto encoder, that actually is fed back to the switching decoder. And the output which we saw here, which was a better output, was actually generated by this network. Now, this is going down further into the detail, like how the hierarchical encoder is. Let me see, from, in the interest of time, should I go in detail? But basically here, as you say, these are like stacked LXTMs. You may be familiar with like how the, what is the equation for basically the reset gate, input gate, and the new gate. The same way, I think the more important part here is that the instantiated RNN for movie sentiment analysis. So here this is the switching element where you have the seeker's answer and you have the recommender's answer. Seeker's answer is basically what the user was expecting. So this is where what the seeker was expecting. Now, I think the other parts are self-explanatory, autoencoder, and also so this is more this is the autoencoder, and this is just the decoder part. So now I'll after covering basic of one deep conversational system, now we'll talk about other methods which are solely based on RL. So one of the areas where the conversational system could be very useful is in the e-commerce application, where on the website you can ask the system, is the battery good? Does it support the dual SIM? Or you can, or show me some red phones, or show me a phone which is less than this. So many kind of interactions people can do with the system, and the system will be able to understand and then can help in even decision making also. And because this is not a standard recommendation system, it is interacting with the user. If it doesn't have the capability of learning on the go, then maybe it will frustrate the user more. So basically, what is needed here is that the recommendation process, as you have seen, is a sequential decision problem, what we saw earlier, and it can be modeled as MDP, which I covered in the conceptual part. And we have to acquire the adaptive strategy because otherwise the user will be frustrated and we will not provide the input what the user was asking for. And again, the optimal strategy, the system is learning by observing the consequences of the actions on the user and also the final outcome of the recommendation. So as we have seen earlier, that if the action was good, then you'll get good reward. If the action is not good, you will not get the good reward. And also the final outcome is important because the in case of reinforcement learning, the final outcome has you get the large reward when you're on the final outcome. So the final outcome is also important. So what they've done is try to formulate this problem as the reinforcement learning problem. Now here what is sorry, the name question?
There was an echo, that's it.
Okay. Okay, so the strategy for learning should be that we extract the plan of the action with the system employees. So this is similar to what we saw earlier. It is like a model which is in agent's mind. And there are two strategies which could be adopted. One is the start querying the user about her preferences and acquire enough information from her, and then select the candidate set instead of just directly based on a standard attributes with the standard recommendation systems do. Here, the RL based approaches will emphasize more onto this part, try to get the preferences of the user. Then the second strategy will be that you can initially propose some candidate. So in this case, the candidate were not presented, but in the second strategy, what could be done is, then we can propose some candidates and acquire some user preferences, and then basically personalize the future recommendation. So these are the two strategies which are being deployed. And the policies are learned when the agent estimates in a different way. So with this is what I mentioned earlier, cost of each interaction. So we don't want to disappoint the user. So, so that's where we want to know really good about what the preferences are. And that again, which we mentioned earlier, the discount rate parameters, the probability of being willing to continue the interaction. So the user's probability of interacting with the agent will be high very initially. So just have to keep that in mind for the particular recommendation which was provided at this stage. So the adaptive recommendation model basically has two components. One is the information system, and the second one is the recommendation agent. And this information system is typically the standard recommendation system, which are not adaptive, don't get any input from the users, what is to be done. And here, in case of a recommendation agent, it will observe what the user is asking, and also what the user's reply is, more of what is the interaction, and so that it obtains the right information at the right time. Now, so this is more of an analogy where how does this happen in the normal world? Is that a traveler basically browses the course catalog, and then it gets transferred to the travel agent, and then travel agent further finds the suitable products by asking the question. So this is an analogy which you can consider for these two boxes which are presented. So here, one thing, these two I already covered. I think this is more important point here. Measure the personalization impact by determining the user satisfaction with this offering. So what the system try to does it, that not only just provide the recommendation, but also see what will be the satisfaction of the user, and whichever responses will have more satisfaction, those are presented. So basically, in that case, looking at all the summary, what comes up is that our goal is to learn the best strategy to deliver personalized offering to the user, decide when to push recommendation, or decide when to acquire some information from the user, or show the most popular products. So then we will get to the further detail about the way we saw how an RL system is modeled. So here in this case, the agent interacts with the user who is part of the environment. So here, this is the recommendation agent, which is the policy, and the environment is basically the user. So here the role is flipped now. So our recommendation system is a policy, and the environment it is trying to understand what is there in the user's mind. So the agent observes different aspects of the environment state, or basically user state, and takes what it believes to be the best system action in the state. So let us say we start with here. So during first state, when the environment is in state 0, the agent decides to take action A0. And after it has taken action A0, it is presented, it knows what is the reward it got, and then it moves to the state 1. Then at state 1, again it takes action A1 and then goes to the and gets the reward R1 and then goes to state 2. So this is how basically in iterative way the system actually learns. And one very important point here is that in reinforcement learning, that the agent environment interacts as the agent environment interaction session proceeds, the way I am showing here, the agent would eventually learn to make the best actions for all the possible environment state and would help hence adopt optimal policy. So it is guaranteed that we will learn when the agent is interacting with the user for a long amount of time and in various scenarios. This system is going to learn optimal policy, which is basically of all the policies, which is the best policy. So that in future, in the prediction time next time, when something has to be presented back, the system will use the optimal policy and revert back to the user. So then what is the optimal policy? So optimal policy is like which is maximizing the expected cumulative reward. So I skipped that slide earlier, but basically optimal policy is that whichever path, whichever policy is having the maximum reward, that is one will be chosen, because minimum reward one will be is a not effective one. Again, there is one more important that so what happens is that how many times the interaction will happen, that information is not known to us. The agent may interact with user once, twice, thrice. So we don't know how many times. So what is being done while modeling is I think I covered history, and the opposite of history is a horizon in future. So how many steps the system could go, and because we don't have any fixed amount, so what is being done in RL is that we basically computed for the infinite horizon discounted model. And it will not hurt, because if the discount factor is like less than 1, the more states which are in future will anyway be having very diminishing effect. So this is the reward which I was mentioning here. And if you see the equation is not that complicated. Basically, you're talking about from timestamp from 0 to infinity, and you are taking all rewards and weighing them with respect to the discount which is there. Yeah, so I think this is I think the most heavy mathematical slide, but so here up to this, I hope you're able to follow that the agent is having certain policy in mind and interacts with the user. And because we don't know how many interactions will happen, so that's the summary. The policy will consider all future horizons with this equation. Okay, so then so policy is written as pi. So let us say the agent here is following some policy in the beginning, let's say pi 0 or pi 1, and then it will then keep on updating it. So the value of the state under S. So basically what happens is that so I'm just trying to take you back. So value of a state under policy S is what I'm trying to explain. V pi S. Yeah, this one. So, so here, let us say if we talk about this, if we talk about this particular state, if the policy is like the shortest path policy, the optimal path was this going here and here. So this was the optimal path. So the value of this state when we followed the optimal policy will be higher. Then If we come to this state, come here, go here, all the way, we struggle all the way, then again come back and again come to the same state. So what we have done is we are like done unnecessary effort. There's a lot of penalty on the way. So in this case, the value of this particular state under the second policy where we went down is basically a very different and very, very low. So that is what this V pi S means here. So you will see this kind of notations in the papers. So that's the reason I'm just trying to explain it a little more detail. So V pi S. So this is what we are saying is the value of the state S, which is this value of the state S under the policy pi. Okay. So this is the expected cumulative reward which the agents receive when it starts in S and follows pi thereafter. So hope it is clear. Maybe. I'm just doing some changes right now so that. So hope now this slide is simpler and clearer. Then going back to the further. Now this V pi as in case of MDP, I think we don't have to, maybe I can skip a lot of mathematical part from here. So basically in summary, what we are saying is that the optimal value is unique and is the solution of the equation. So based on this, we'll get, because of there are multiple policies, we'll get multiple equations. And the optimal value is unique and its solution, and the solution of the equation is this. And the optimal policy is given by this. I think summary of this slide is the policy, optimal policy which you'll get is given by argmax of all the policies which you got. And then basically, this is what you will try to learn from using the system. Now there is one, you may know, like in case of iterative approaches, basically what is being done is that you evaluate a policy and then see, in case of evaluation, you basically compute the value function for the policy. And then in case of policy improvement, the agent uses the computed value to improve the policy. So here the value function is computed. And then here in this case, basically the policy is improved based on the new value function which you got. So for example, here, how do you learn the, how do you improve the policy? So when you are here in the first time, and then when you are here again at the same place at the second time, then in that case, you just want to find the value function, and then you try to iterate it. So basically it goes into the iterative mode. And this process is repeated for all the states. So this happens in all the state, not in one state. And if the improvements occurs, then a new run starts and the new policy is evaluated and then improved. So this is how, so this is what was about the first paper. I think I'll skip some of, or maybe let me go through this paper completely. So here, now this is an example of a website where people just provide the general travel preferences. And the current system was basically using interactive query management technology. And what it was doing is that, let's say if the people select all these recommendations, and then if we get if in a situation where we get too many, products are retrieved, and we don't want to provide hundreds of products. So the approach what was taken here is that should we tighten the query in the sense that so it will help us in reducing the size of the retrieved set or basically the result size. So let us say if the user selects and there are 48 results which are there, and then if you want to tighten the query, then you will basically, or then in that case you will have the limited results available. So this is what the tightening the query mean. And now here In some cases, user may be okay that let's say after tightening the query, you provided 5 recommendations, and the user is okay with that. And then in that case, it is accepted. Otherwise, the user will go ahead and click on some of these filters on his own again, and then try to expand it further. So this is what was applied in this. And then now, as we have seen earlier, that in case of Markov chain, basically what are these nodes and what are these arrows? So here basically S is the starting page, QF is the query form page. So this is the query form page, and this one is the tightening page, and this is the resulting page. So this is how basically the interaction is modeled in the Markov chain. For taking, let us say, this website as an example, how it will actually be modeled there. And the other one was, so this basically describes the actions of the system. So how the system will go, because it is like system which is moving, not the user. So this state diagram is for system. So you start page, query page, and then query form page, and then tightening page, and then results page, and then the exit page. But if you talk about the user, now in case of user, the user can take multiple actions. I'll not go into the detail, but this is how the various actions which are taken by the user. So those are represented by arrows, and the nodes are basically what the user state will be. So this is how a system is basically modeled. So I just wanted to, I taken this as an example with a little bit more detail, so that in the future papers, it will be easier to briefly go further. So now I'll talk about the personalized conversational agent here. And now the focus is like single round means that the user, we got some input from the user, the system replied, and the user either accepted or not accepted. But in case of traditional, even if the user has not accepted, there is a possibility that maybe is trying to look for something else. So this is kind of a multi-round dialogue system. And this is actually more complex than single round. And so here basically we're talking about like improving sales. So we just want to know the users, learn the user preference, and also the past purchasing behavior, and also optimize the business-oriented metrics. So this is the goal of the conversational recommendation system. Now here we are talking about deep reinforcement learning. So sorry, I didn't mention one thing, that what is reinforcement learning and what is deep reinforcement learning. So basically all the value functions which are mentioned here, all these value functions which are mentioned here, this in case of this function approximation, you can go through MDP and do the function approximation, or you can even use the neural network also, because neural networks are capable of modeling any kind of function approximation. So when that is being done using the neural network, so that is where it is called the deep reinforcement learning. So basically, in case of deep reinforcement, we are learning the values of various functions using neural network. So this is the conversational recommender system. Now here we are using the deep reinforcement learning. So here basically what is being done, the ranking and personalization which is being done in the traditional recommender system, along with the sequential decision making power of reinforcement learning models. So here, how we will do it is then analyze what the user has said in the current session, and interactively ask user clarifying questions, and make personalized recommendation when the system feels that, oh, it has got enough information from the user for now I can provide the recommendation. I am more confident about it based on the current session and what the user has consumed before based on his history. Now, to achieve this, there are 3 basic questions which the system has to think through or plan for. One is how to understand the user's intentions correctly, and how to make sequential decisions and take appropriate actions, and then how to make personal recommendation. So recommendation actually comes later. First, basically, we just want to understand the user's intention. So here, the system has basically three components. This is the belief tracker, policy network, and the recommender system. So here, the user basically talks to the belief tracker, and at timestamp, the user say, I want to find a bar. And then the framework calls the belief tracker to convert the utterance into a vector representation or belief. So basically, belief is that it is not the exactly I want to find a bar. It's transformation, maybe a vector representation or a belief. It is converted into that. And then this belief is being sent to the policy network to make decision. So basically here some kind of higher level abstraction or more understanding is being done by the belief tracker, rather than just by, passing directly, I want to find a bar, either it's embedding or the text in some form to the policy network. So for example, here, what the system could feel is that, oh, if the person has asked about the bar, then maybe at least we need to know about the city in which, rather than just suggesting some bar. So this is an example here which says that the belief network may request city information also. And then the agent may respond that which city you are in. So instead of just directly answering the about the bar, because of the belief tracker component, we are asking the right next question, which is which city in you live. And then the agent calls the recommendation system to get the, once this city information is available, then in that case, we invoke the recommendation system and then provide the recommendations. So this is a very high level view of the conversational system based on RL. Now here, this may look a little overwhelming, but it will be, I'll go through slowly. So in case of a unified deep reinforcement learning framework to build a personal conversation recommendation, we basically go through following steps. So basically represent a user conversation history as a semi-structured user query with facet values. So basically we convert the conversation into semi-structured user query, which is what the and then this query is generated and updated by belief tracker. So basically, this is like more detail about what I mentioned here, what belief tracker was doing. That analyzes the natural language utterances and of the user at each step. So basically, because it understood that is talking about bar and finding a bar, the belief tracker actually went one step ahead and tried to understand what the natural language utterance was. And then basically try to train a deep policy network to decide which action the agent should take. So this is the deep policy network. Then it comes here, and then it decides what is the next step the agent should take. And train a personalized recommendation model that uses both the user's pass rating and the user query collected in the current conversation. So it is basically this this module which I mentioned earlier. So this is the recommender module. When making reading prediction and generating recommendations, now tries to collect the user preference by asking questions. And here, again, this is the way it asks the question, that in which city you are in before providing any recommendation. And also once the enough user preference was collected, it makes the personal recommendations to the user. So then I'll go into the details of belief tracker, recommender system, and the deep policy network. So, so this is the structure. Now here, as you see, these are the three modules: belief tracker, policy network, and recommender. We'll double click on that. So this was the function which we already saw. Belief tracker system understand which values of the user has provided for the product facet and represent the user utterances with a semi-structured query. Now it is extracting the facet value pairs from the user utterances and also maintains the facet value pairs in the memory. So it is even let's say in this particular conversation, if the user has said something like a few turns ago, the system has still it in the memory. Like dumb conversations, even though somebody might have asked the same thing previously or mentioned same thing previously, the dumb system will actually repeat and will not know that the interaction already happened and I should be smarter. So that is the reason it actually keeps it in the memory. And then we have the product facet or attribute. It keeps as the facet value pair here, facets and value. So I think, yeah. So facet value pair, why is it important? Is that if the person says color, I want red color t-shirt, then I think with t-shirt it becomes very important, the red facet value also, facet and its value. So facet is color and its value is red. Both are available. So the belief tracker then takes the current and the past user utterances as input and outputs a probability distribution across all possible values of a facet at the current time. So mathematically, if you see what is given in the paper is that ET is the user utterance and ZT is the sequence of n-gram up to the current time. So ZT, what is here is basically the sequence of all the utterances which have happened till this time. And the output of LSTM is the hidden representation HT. And then you will have the softmax over it. So FT is the softmax there. And then ST layer, what is the output of belief tracker is that Fi are concatenated to each other to form agent's current belief, because there are various beliefs at various stages. So all F1s are combined. And then these are all concatenated, and then ST is basically the current belief. So this is how the belief tracker works. Now here there was no RL component, but in case of recommendation also there is no RL component. RL component is basically as part of the policy network model. Let me still quickly cover the recommender model here for the sake of completeness. So as the conversational system interacts with the user, as certain round the conversational system decide to make a recommendation system based on its current belief of the user information need. So this is what I mentioned here earlier here also. The recommendation will happen once we know that if information is available from the user, and the recommendation system is trained with the dialog state, user information, and the item information. So usually in the traditional recommender systems, you will only have user information or the item information, but here we are combining the dialog state also. And factorization machine is one of the ways of doing it, which has been used in recommendation system. Now let me move on to the last module, which is the deep policy network in this particular paper. This is based on the RL. This is an RL component. So here RL model selects an action based on the dialog state. And now which action? So if you see how this completes the picture, this is what we are referring to as an action. So this is the policy network RL based component. It will take an action, but for it to take that action, what is it that it will do? So just give me a minute, I'll just have water. Maybe it's a good time to ask, is it clear? Is everything going smoothly? Is the speed okay? Or should I repeat something? Any feedback?
Yeah, there are a couple of questions from my end, but yeah, I also asked the audience if they need any questions, if they have any questions. So the one was about an earlier part of your slide where you actually talk about the negative rewards. So the question is like, and we have like positive rewards and how that would affect the outcome in terms of like the policy. And then is there like any memory efficiency analysis that's done, check if these models take a lot of space, and then if there is any discussion on like compressing these models? Okay.
Sure. Okay. So basically, I'll right now answer the first question and the memory efficiency. And what are the second question? Third question after memory efficiency?
Oh, the first question was about the rewards itself, like when
Yeah, I'm
in
saying, so
figure,
what
like
is the third question?
there were only two questions. The third
Okay.
question was general about like the slides. Like will the slides be shared as PDF if they need, but
Yeah, yeah,
I'll
definitely. It will
be
be shared as
recording.
PDF. Yeah, yeah. Yeah, I
Okay.
have the link at the end. Yeah, it will be shared. Okay. So from
Yeah. If there is any question in the room, just raise your hand and I'll bring you the microphone. Sorry to interrupt you.
no, that's fine. I think yeah, I had also taken kind of break. So so basically, yeah, usually in case of reward, you can term anything, right? You can say all negatives are like penalty or negative rewards, and 0 is a positive reward. So in case of reinforcement learning, usually you get the benefit only if you achieve the end goal. So like at all other places, you'll get -1 reward, but once you hit a goal or once you get a goal in a game, then you'll get 100 points. So that is how it is being done. So there are no positive, they don't call it positive reward or negative reward. It's value, which is like relative. That is how you can take it. So rewards are always higher value rewards are better and lower ones are like not good. So that's how the terminology is used there. From memory efficiency analysis point of view, we'll try to cover later if we have time.
Sure. Yeah.
Yeah, and the slides will be available. I have the link toward the end. Okay. So now in this particular module, again, so it's not that I recommend, I just wanted to mention that why I took first example as the classical or deep conversational recommender system, how it can be built. So whole thing cannot be like completely RL. There are like traditional components also, which will be part of it. And this paper highlights that fact. So in case of a deep policy network, basically, at each turn, what the RL model has to done is that it has to select an action based on the dialog state so that the long-term returns are maximized. And again, here in an RL, we're always talking about long-term return. We're not even if we take a bad step in the beginning, maybe it will lead to a like proper long path. So that's the reason we always talk about the long-term return. And here the policy is learned, like what is the policy which we should be using in future when we have to respond to the user. So some of these things may sound repetitive, the state, action, and reward, but I'll go through it. If for some people this is like the first session, then it will be a good follow-up on the paper. So state is basically the current description of the environment from the viewpoint of the agent. And in case of conversational context, in belief tracker, what we do is that whatever all the conversations text which has happened, we just concatenate them. So that is basically the state. And action is the decision the agent takes at the timestamp t. And the agent takes two type of actions. One is that basically keep asking questions, keep asking clarifying questions. So basically request the value of the facet. So like which city you live. So city was facet and value some let's say Seattle is like its value. So keep request the value of a particular facet which he feels is needed. And then once all the right facets are there, then make the personalized recommendation in this case, and then the recommendation module will be called. A reward in this case is the like benefit or penalty that the agent gets for interacting with its environment. So according to the current state T, action 80 is chosen following the policy, and it gets the reward RT and denoting how good the current session is. So the state transits from ST, current state, to the SDate state. And the conversational system gets a reward when it requests a facet value or makes a recommendation. So when the conversational system, in all other cases, it doesn't get any reward. You can term it as 0. And in other cases, you can term it as any positive number. Now, how this is being achieved is, as I mentioned earlier, now it has to learn policy. So the policy is basically denoted by pi. So if I am in state A, state T, what is the action that I should take? So the policy represents the score as the probability of taking action when it is in state T. So the publishers of this paper actually went ahead with only 2 fully connected layers as the policy network. So this is what I mentioned earlier also, that traditionally, when we use the neural networks for learning the approximation function, and then that is the deep reinforcement learning. And here there are 2 fully connected layers which are there as a policy. You see here W1 and W2, and with the ReLU activation function. And then the output of this is actually sent to the softmax layer, and we see what is the best possible action. So here the goal of the policy. So I think that this architecture is clear. And then the goal of the policy network is to maximize the episodic expected reward. So here, basically, maybe we may not get into this. So now there are further announcement which was done. They call it the reinforce algorithm. So the way we try to do the learn the optimal value by using the gradient. So in the same way, what is being done is that whatever the expected reward function was, takes its gradient and then try to optimize it. So this algorithm has been used universally. The summary is that here basically you take the gradient and then try to learn. And here GT is same as the sum of the rewards or the returns which you mentioned earlier. People use rewards and return interchangeably, but return is basically the cumulative reward, and from whichever state you were and going forward up to infinite horizon. So what are the terminating conditions? The terminate the state of the conversation, either when the user leaves the chat, or the system feels that I got the information, I recommended the item successfully. So such kind of sequences are also called episodes in reinforcement learning. So again, the previous history, so sequence, I'd mentioned earlier, like sequences, those are also called episodes. So what are the various episodes, various trials which can be done by the system? So then I can move on to the one more paper. I think I had allocated 90 minutes for this, but the slot which I have given is like for 3 hours. So maybe I can go a little over. So is everyone fine in going over?
Yes, I think that should be okay.
Okay, yeah.
There is someone who's raising an question for you.
Yeah, because I'm not, when I'm presenting slides, so maybe. Okay.
Yeah, there's someone who has a raised hand who wants to ask a question.
Can I ask the question through voice? For some reason, my chat is not working well.
Okay,
Sure.
that's.
So when do you train the model? Is that when you start chatting, or when you with the customer, or is that depending on the data? I just don't understand.
It's a good question, and I think in concept part, I did include the online learning and the offline learning. So basically, in case of let's say any chat, we cannot just put the RL-based recommender system, and then it is just trying to learn right from beginning at the cost of like various interactions which happen. So basically, what is done is that we have the offline chat history which is available. On that, you start with like a policy, initial policy, and learn some policy. And then what we could do is that whatever the partially learned policy RL agent is available, Then we can put it in the online mode, and then it can start interacting with the users and then further improve the policy. Thanks for asking the question. Does that answer the question?
Yes, answers my question. Thank you so much.
Yeah, and thanks for asking, because I think I missed out the offline online part of there. Okay.
There are a couple of questions here in presence. Just let me bring the microphone to.
Yeah, and in RL network, in RL terminology, like doing the training offline is called planning. Yeah.
Thank you. I just want to follow up the previous question. So when you mentioned the like online learning, is that like the basically how do you determine the frequency of that learning? Like also that mean the policy will not be optimized at the beginning, and do you expect that to be optimized at a certain stage, or in another worst scenario, it may never be optimized because the environment may not be stable?
So yeah, I got your point. I think the partially your answer I covered partially is that from the previous existing logs, we will start with the like initial policy, no policy, and learn offline on that. And when we have some reasonable policy, and then in that case, you can go online. And in case of online, as you mentioned, you can decide how basically you want to, how frequently you want to update the policy.
Okay, so is that under the assumption that the environment has to be stable, right? So if otherwise your policy may have to be like not converted to the optimal state.
Yeah, agree. Yeah, because if the environment is not stable, then the system will keep flipping and learn different things at different times. Yeah.
Okay, thank you. I have another fun, very general question regarding reinforcement learning. Like when you at the beginning in your presentation, you said there was kind of a 3 big component in the reinforcement learning: policy, value function, and model representation, right? So and the model representation, I think, is that a necessary part? Yeah, here, yeah, agent representation of the environment. Is that a necessary? Because sometimes we really don't know how to represent the environment.
So this will become more obvious in case of offline setup, right? So basically, when you have like offline chats which are available to you, okay. So this is what is happening is like in real time, right? The agent is taking action, environment is throwing some state and reward, and then it's keep on going. It's making some model about it in the mind. But there is a model. So I think model will more come into picture when you're talking about offline setting.
Sorry, what is model here in this case?
A model is here. A model predicts the what environment will do next. So it's like our in our case also, like if you talk about traditional system, it's like more of a trained system. You have the trained model now, and then that will be used to predict what.
So you have so in basic, the very fundamental requirement for the model, because you need to build whatever model, right? Probability prediction, whatever way, and you have to model the environment, right?
Yeah.
And you cannot just treat it as a black box.
Yeah.
Okay. All right. Thank you. Yeah.
Yeah, and there is one more.
Yeah, sure.
Hello.
Yeah.
I have 2 questions. So firstly, you mentioned offline and online training are both utilized for the previous paper, and but you also mentioned using reinforce, which is on policy, right? So how do you use that for offline setting? Do you use something like importance weighting?
So I was not, when I was answering, I was not very specifically referring to that particular paper. It was a general reinforcement learning statement I made.
So you mean like reinforce just like a general approach, just mentioning as general
this one,
approach
right?
here.
Yeah.
So for the offline setting, how do you use reinforce since it's a on policy algorithm?
So I'll have to check this particular paper further, whether they're going ahead on the offline part or not.
So if I'm not sure, I have another question about the rewards. So for the conversational bots, like I get, I guess that most likely you have like a success failure outcome at the end, whether the customer's problem is solved. So the reward can be very sparse, but so how do you actually formulate the rewards for such a problem? Like make it denser? Meaning like getting like non-zero rewards for each step.
So here, if you take an example here, the paper which we discussed. So here you get the reward upon the successful recommendation toward the end, right? Or the user leaves the chat. This is more of a terminating condition, right? Now your question is that the reward is sparse, and how do we represent it, right? Is that the question?
Yeah, just want to get some ideas like how for the formulation.
Let me think about it. I'll come back to it later.
Sure. Yeah. Thank you.
Yeah. Yeah.
Is there any other question? Okay, I think we are good. Thank you.
Thanks. So the next one is the paper for estimation, action, and reflection, EAR. They call it as abbreviation. And again, you get the similar concept is used here. You get the user preferences from the, you get the user preferences dynamically. And then, so here there are three fundamental aspects which the CRS has to consider. What questions to ask regarding attributes, and when to recommend items, and how to adapt to the users online feedback. Now, it basically, to achieve this, it is broken into three components. So estimation, which builds the productive model to estimate user preferences on both items and item attributes. An action, which learns the dialog policy to determine whether to ask the attribute or recommend the items. So here, basically, there are two outcomes only. Should I ask the question or should I recommend the item? Only two states. And reflection is the update the recommendation model when a user rejects the recommendation made by the action stage. So whenever, because if the user is rejecting, that's a very strong signal, and that needs to be incorporated. So here basically there are two components. One is the conversational component and the recommender component. So conversational component is responsible for interacting with the user, and a recommender component is responsible for estimating the user preference. Now, the questions which we discussed earlier, like what attributes to ask, here the idea is that we want to hit the right item with the fewer turns. So it needs to consider which attributes to basically ask. And this is exactly the job of the recommender component, which scrutinizes users' historical behavior and then adopts. And then when to recommend the items. Again, when the system is sufficient certain, the conversational component is certain, then it could push for the recommendation generation. The good timing for recommendation generations are when the candidate space is small, and the thing which has to be kept in mind is that you don't want to ask you have to keep in mind how much information you will gain by asking, and also will you be satisfying the user or dissatisfying the user. And the recommendation component is like when it is confident that what are the top recommendations which it is generating will actually be acceptable by the user. Again, the next point was that how to basically adopt to the user's online feedback. So in case of estimation, it builds the model offline to estimate the user preferences on items and item attributes. And FM is used using user profile and item attributes. The action learns the conversational strategy, determines whether to ask or recommend, and train a policy. So again, as I mentioned earlier, this is the component which uses the RL technique. Train a policy network with reinforcement learning, optimize the reward for shorter returns and successful recommendations based on the previous components estimates, and reflection specifically when the user rejects the recommended item, construct a new training template by treating the item as negative instance and update the factorization machine in online manner. So here basically the two actions which the system is supposed to predict: should I ask or should I recommend? And CRS may ask 0 to many questions before making any recommendation. A session terminates if the user accepts the recommendation or leaves due to his impatience. So the goal of CRS is to make this desired recommendation with as few as rounds possible. So I'll skip this part. This is more of a traditional Bayesian personal ranking and other methods and multitasking. You can look at the slide later. So in case of action, the reinforcement learning is used to tackle the multi-round decision-making problem, aiming to accomplish successful recommendation in short-term terms. And so basically the state vector is encode the information from recommendation component and dialogue history into the state vector, providing the conversational component to choose the action. And here these are the four perspective which are being taken while considering it. So the SENT vector basically represent the entropy information. S-pre covers the user's preferences, and his is the conversation history, and length is the length of the current candidate list, and these are all concatenated and used for finding the best strategy. Now here, in case of policy network, there are these type of, again here, the policy network is simple. It is a two-layer, multi-layer perceptron optimized with the standard policy gradient method. It contains two fully connected layers and maps the state vectors into the action space. And the output is again normalized by the probability distribution overall actions by softmax. And the rewards which are considered, I'll just mention the rewards. And so strongly positive, this is like R success is a strongly positive reward. R ask is a asking reward. R quit is a strong negative reward. And R previous is like the slightly negative reward. So the intermediate reward will be the sum of all these four rewards. And policy network will basically the policy pie which determines the probability of taking action at given state, ST, and optimize the policy network, use the standard policy gradient method. So previous theta minus the gradient into the learning rate. And RT is the total accumulating reward from turn T to the final T. So from turn T to the final T. And as I mentioned earlier, gamma is the discounted factor, which goes with the reward. And in case of, sorry, there is one thing which was missing. Yeah, so here I think there is one. So the succession, when we say strong, so this number will be higher. And when we say quit, and this number will be higher. And ask and this one ask will be the lower numbers. So this is how the weighted reward will be calculated. And reflection is again more of a standard recommender method. I'll skip this. This is a part of the slide, but again, I had included that this is not based on RL, but CRS using traditional methods. Not traditional, you can call it deep method, but not deep reinforcement method, because here what is being done is that for predict. So here, in this case, the goal is to generate proper responses to the user for topic guidance or item recommendation. And here the user's text data, all kind of text data is being used. So historical utterances are considered combined into the conversational BERT, historical topic sequences combined into the topic BERT, and the profiles is converted into the profile BERT. And then those are being used to generate the topic, to predict the topic. And response generation is like typical using, it is using GPT for doing it. I just included because this had more of a recent approaches, BERT-based approaches for topic guided conversational recommendation systems. So again, I think there is one more which I listed in the presentation is the path reasoning. And I'll not get into the detail, but I think the key thing here to mention is that it is very explicitly explainable. So because it is based on graph, whatever the path which is being taken, and each step is basically confirmed by the user. So in that case, explainability is like inbuilt when you are using this approach. And that is the reason the resultant path is the correct reason for the recommendation system. And you can use it uses the fine grained attribute preferences also very well in terms of explainability. And because it is a graph, it helps in facilitating the exploitation of the abundant information, because you can limit the candidate attributes to the adjacent attributes. Just to mention the terminology here, what I was meaning by that is that light orange are basically the users, alias Thomas, and light blue are basically the attributes like block party or Simon Powder Station, Michael Jackson. And the light gold items are basically are the items. So for, if you take an example of artist Michael Johnson, it is an item and it has attributes which are rock and dance. So because in case of graphical representation, these advantages which I mentioned, clearly explainable, explainability is inbuilt, exploration is easy, and also you are able to combine naturally the conversation system and the recommendation system. Both can be combined in a natural way. So this paper talks about it.
Is it a good time to ask question?
Yeah, I think I'm done. Just a minute. So.
Okay. Yeah, so there is a question in the chat from Omar. It says, what's the difference between historic utterances and historic sequence?
Sorry.
So there's a question from Omar. The question is, what's the difference between historic utterances and historic sequences?
Historical utterances and,
Historic sequences.
sorry, I'm not getting the last part. Historic
Sequences.
sequences. Okay. Yeah. So basically, when we talk about the reinforcement learning, the CRS, which is very specific to text, then in that case, whatever the previous, let me just use what items or the steps which were taken, which were like the text utterances which were spoken earlier. So the previous utterances are very specific of previous sequences. Now sequence, if you talk about sequences like in a video game, if you are moving north, south, east, west, that is like a sequence, or in any other case, or in another way, right? So sequence is more of a generic term. Sequence can contain anything, and previous utterances mean that sequence was of utterances. Does that help?
Yes, that is clear. Thanks.
Okay.
Does anyone else have any questions for Om?
So I included references at the end, and this is the website where I'll upload the, if you have any questions, you can send me email here, and I'll be posting the slides on this website. Are there any other questions?
Yeah, there is a question here in presence.
Yeah.
Could you explain a little bit on the policy network output in that previous presentation, like in the recommended system setup? What is the policy like network output? Like in general sense, is should generate the output of the policy will be action, but in that model you just explained, what is the action in that specific setting?
Just let me see which ones you are referring to.
In that three piece model, one is the what they call the belief
Okay.
policy and the recommender. Yeah. That. So what is the output? Exactly output regarding in the to recommend the final items.
Okay.
Yeah, in this slide, basically AI seems output, but how to interpret that is what exactly, like use the language in the recommender system, what does that exactly represent?
So basically, I think that was come somewhere earlier. So here the action, so A is action. Okay. Now the action is that there are only two type of actions which are possible. One is either you recommend or you ask further questions. Now in asking further question, what do we basically want to know is that for which particular facet we ask the question. So if you see this example here, when the person had entered bar, the action came out was that for a facet CT, we need to get the value. Okay. So here the action is, so find out the value for a facet. So what the moment the output of this policy network is like any of the facets, and in that case, basically what we are telling the model is that ask its value to the user. Or if let us say we have, or the action could be, no, just do the recommendation. So the A will be two, one is the different facets, or just make recommendation. Does that answer your
Okay,
question?
okay. Yeah. That's what I need. Thank you.
Okay, yeah, thanks.
Is there any other question?
I have a question. How many LSTM networks you need to put in the belief tracker?
So again, it will depend a lot on what kind of utterances you are having and how long basically you want to do the concatenation. So this is more of a standard, any kind of representation which you want to generate, or you're building a model based on RNN or LSTMs, right?
So can we say that this is
refer to the paper for more detail, because I didn't go for.
Oh, okay.
But again, depending upon the application, let us say if you are having a very short voice assistant, then you're expecting only a few words to be spoken. But if you're talking about like some kind of where the users are typing long queries, then in that case, the number of LSTMs which you will need will be more. So it will depend upon the how, and then how much of text basically you want to develop the context over, like typical LSTM hyperparameter.
Okay.
Yeah.
I'm sorry, do you mind if you can repeat the W1, W2 part? I didn't understand where it comes from.
Definitely. So basically, in case of policy, here. So here basically what happens is that the output of belief tracker, okay, will come to the first layer, which is the neural network, layer 1. And it has ReLU as the activation. Then your additional neural network W2 layer, and it has ReLU as an activation. So this is like 2 feed for all neural networks which are here. So the output of belief tracker is fed to 2 feed for all neural networks, which has 2 fully connected neural networks are as the part of the policy network, and then output of it is basically the for softmax is taken over it, and then AT is generated. Does that help? It's a simple 2. You can assume it is more of a simple 2 feed for a 2-layer feed for a network with softmax on top of it.
Yeah, makes sense. Thanks.
Does anyone else have any questions for Om?
We have a question here from Presence.
Yeah, sure.
Hello? Yeah.
Yeah.
I have a question about some real-world application. Has this approach been ever tested or tried in some application?
Yeah, definitely. I think some of the papers which are listed, they have tried it in the real world. Let me see. Yeah, and there are results also available from real world. One example which I can give from like the previous RecSys conference was that in case of you mean conversational recommendation, right? Not general recommendation.
Yeah, the conversational RSS.
No, then I think I was going to example of general recommendation. I'll have to check that, but because you're right. I think this area is not explored that much. Only very few papers and very few approaches have been taken up. And what I saw was on the like publicly available data set. So I'll have to dig further to see which paper really talks about a real world situation where they had improved it. I didn't come across it when I had gone through it.
I have a follow-up question on this one too. So you're saying that it was more tested on general recommendation rather than the conversational?
Yeah. General recommendation, yes, it is. I think there is a paper from Google where they had, I think Ming was the person she presented, and Google was doing recommendation system with various approaches. And that approach actually surpassed all the approaches which were taken in the previous 2 years.
Okay, so then how the utterances are replaced? Like there is no consideration of feedback from the user using utterance, right? So how did they replace that?
So I think this is what I distinguished when I was answering the question. When I'm saying general recommendation, that means there is no text or these things are involved. It's a standard ID or item features, your user features and other kind of information, side information. It is not natural language based. In that scenario, Google had significant gain for using RL. What I was saying is that in case of conversational, because language itself is very tricky to understand. So from conversational recommendation system and also applying RL on it, I think whatever search I had done, I could not find any. Maybe I missed on some of the papers which we were talking about real world, but mostly they were.
Yeah, makes sense. Thanks.
Yeah. Yeah.
Well, yeah, I have a question about the evaluation. So that is, how do you evaluate the quality of these systems? I mean, definitely you can evaluate the quality of the recommendations, but also it also depends on how many conversations we need. For example, sometimes we are able to derive recommendations based on just 2 conversations. Sometimes you are able to deliver recommendations after 7 or more conversations, right? So this is my first question. Second question is, usually in this CRS, so how many items will you recommend it? So are you going to recommend just, let's see, a single item, or at least, let's see, up to 10 or 5 items?
Okay, sure. So again, your both questions are very specific to what applications you are working on, what data set you have, what kind of text you are having, and how the recommendation page look like. So I'm first answering your second question. So in that case, it will all depend upon the requirement. Typically, in recommendation systems, it will follow the similar approach. What is being done in the standard recommendation system. Also, let's say if you're on your website, you're recommending again, see some of these, let's say 5 items or 10 items, will continue to follow that. So I think using RL will not change how many items you are going to show, because this is more of a user facing thing. To answer your first question, like how many iterations will you need? Again, it depends on the data set and what evaluation you are doing. Yeah, and you also partially answered, like sometimes it can be very quick in few iterations, sometimes it may take time. So it is again very specific on the data set. Does that answer your question?
Thank you.
Yashar, you can ask your question.
Yes, can you hear me?
Yeah.
Okay, so thank you for the nice presentation. My question was basically a summary of basically this tutorial. Basically, what I would like to know is what the specific benefits reinforcement learning and deep reinforcement learning can provide to conversational RecSys, for example, compared to other networks like LSTM, which can also treat this sequence of conversations between user and the system. In particular, the question is very simple. Why RL? What particular benefits RL can provide here? And the second related question is that another aspect that perhaps the RNNs have been somehow developed on is incorporation of item site features. Like now we have multimodal conversational RecSys that can basically integrate images, for example, in the conversation. So for RL, how easy is going to be to integrate these multimodal inputs, images, and basically use it? It seems always text or interactions, feedbacks are the first thing we start with. But in general, I would like to know your opinion about these two relevant questions.
Sure. So I think the first major difference between RL and like you can call it classical machine learning or deep machine learning is that in case of ML or deep learning, there is no trial and error. You have the data and you have the label. I'm saying in mostly cases, it's like you can call it like one way. You have certain things, you have a lot of data, you train it on it, and then you'll be able to have a model, and then which can be used for prediction. Now, in case of reinforcement learning setup is useful where there is no output available from the system. It is trial and error. The system will keep, you can assume it like that, like we keep having every sample after every iteration. So each sample, each interaction is a sample. System will interact and then get the reward, then it will try again. So on the go, it is basically so this is a fundamental difference between other learning and reinforcement learning. So because of that, either feed forward, LSTM, or any other way, those cannot be used, because let's say if you just take an simple LSTM based example, it provides some output, and then after that, if the user is not satisfied, that feedback doesn't get into it again. It is not doing trial and error. I think so. That is the first part. There's a fundamental difference. And the second one is that you're saying multimodal image or all other information. Yes, if that information is useful in understanding what the user's intent is, definitely it can be and it should be incorporated. But if it is not useful in understanding users' intent, but most likely, yes, this information will be useful and can be incorporated, and should be incorporated.
So do you think there are any systems available using RL using images, or they're gonna, for example, Alexa, the newest version of Alexa is multimodal. Basically, it shows as I think it takes as input images, or it shows as output images. So there is some kind of an image-based interaction going on.
Yeah.
And I think more and more chatbots are becoming like this.
Yeah. No, I agree. So the reason I said yes is because, let us say, if someone says that I want to visit some places in London, and or say which is the like first place to visit in London, and instead of like typing anything, I can just send the image of Big Ben, and the system should understand. So that's where I said yes. Wherever it is useful in understanding the interaction, yes, we can use multimodal. The person doesn't have to type, right, literally BIGBEN, but he can just send the image.
Okay, thank you very much for the information and the answer.
Hi, could I ask one question?
Yeah.
Thanks. Yeah, thanks for the great talk. Recently, when I read the paper, like the wisdom paper and the KDD paper for the conversational recommender system, I found they are like implicitly or explicitly assuming that this user has a very clear idea about the attributes associated to the target item. For example, if the user says some answer like, I like this attribute, or the candidates are all from the attributes or from the items associated with this attribute. Or if the user said, I dislike such attributes, so we will remove all the items with these attributes from the candidates pool. So do you think we should use the user answer as a filter, or what's your opinion? Like, if we should think or assume the user have very clear idea about the tags or attributes to the target items, or that's should work as a soft filter. I wonder what's your opinions. Thanks.
Yeah, so just trying to understand when you said that the user has like some attributes and we remove the items which have those attributes. I didn't get that part. Why are you removing those items?
If a user, because the system will ask some question like, do you like this attributes or dislike these attributes?
Yeah.
And then collect some feedback from the user. But
Yeah.
that means the user has a very clear idea about what tags should associated with the target items. But if I imagine that I'm a user, I go to a recommender system. Actually, I have not very clear idea about what I should use or what I should consume in the future. So do you think that's a reasonable assumption, or you think it can be improved in the future?
Well, I think this is a classical case of like noisy labels or noisy inputs from the user, right? So let's say if you're like thousands of users, then the system will have to, what you mentioned was right, that we may have to have some kind of soft filter. But out of, let's say, 1,000 users, how many users are actually by mistake suggesting the system with the wrong or giving to the system the wrong input, right? If that percentage is really high, and in that case, maybe you have to do modeling for the noisy label or the noisy input kind of situation. But if the percentage is really low, it will depend upon the case. And then in that case, maybe we can treat what the user is saying as the correct input and proceed further.
Yeah, thanks.
Any other questions for Om?
Looks like no more questions.
Yes, think so too. Lorenzo,
Okay,
any questions in person?
I don't think so. Is there any other question here? No, I think we are good.
Yeah, I again presented my email and website. Yeah, you can reach out to me. Hey, thank you everyone, and sorry for the hiccup in the initially in the joining.
No, definitely not a problem.
Yeah.
It was
Thank
a
you
great
very much.
presentation. Thank you for the interesting talk.
Thank you for your presentation.
Thanks. Bye.